continued our conversation about closure. What you can observe from week 2 to week 3 is that we did not explicitly define what closure was. We simply talked about the number set, natural numbers, and what operations it was closed under. So whether or not it was closed under exponents, multiplication, division, addition, and subtraction. You can also notice that parentheses is not on this list, and in our conversation about the order of operations, we said that parentheses tells you to multiply, and so it would be a little repetitive to have it on this list along with multiplication. In order to define closure property, we really need to know what information is necessary. So the question that I ask the students is, what information do we need to define closure? If we return back to these examples here, we see that everything is abbreviated, but the natural numbers are closed under exponents because a natural number to a natural power is a natural number. The natural numbers are closed under multiplication because the product of natural numbers is natural. The natural numbers are closed under addition because the sum of natural numbers is natural. And they're not closed under these two operations because the result is not natural. So here for division, we see that the quotient of natural numbers is not natural. It's not always natural. It's rational. And the difference of two natural numbers is not always natural. It's an integer, which includes the positives and negatives. In order to answer the question, what information do we need to define closure, students need to be listening very carefully to the conversation that we've had about the natural numbers and the operations that it's closed under, and also be able to generalize the information that we've been talking about. So, the two pieces of information that we need are a number set, which we've only talked about the natural numbers, so that's a hard generalization to make, and the operations. So the one thing that all of these have in common is that we're talking about operations in each, but again, because we've only talked about one number set, the students typically don't make the connection that they need a number set and an operation to begin a conversation about closure. So here we move to our next number set, which is the integers. We use the symbol Z to represent integers, and we say integers are the natural numbers and their negatives. Here are some examples of integers, but every whole positive and negative number, including 0, is going to be an integers. The question that we ask before we begin is the set of integers closed under each operation? If we look back to the set of natural numbers, we saw that natural numbers were closed under exponents, multiplication, and addition, and we want to see if the integers are closed under the same operations or more. Here we have addition, and we see that z plus z equals z, but again, what I want the students to say is that the integers are closed under addition because the sum, the result of addition, of integers is an integer, and it's actually always an integer. Now, students will do example after example, but eventually they're able to generalize this. For subtraction, most students will say, no, it's not closed under subtraction. The integers are not closed under subtraction. But as they look a little closer and they begin to understand what it means to be closed, they say, oh yeah, when I take two integers and subtract them from each other, the difference of integers is going to be another integer, because I'm always going to get a positive or a negative whole number, or 0. For multiplication, the students see that z times z equals z, which says the integers are closed under multiplication because the product of integers is an integer, and after example, we see this to be true. But then we move to division. So, for division, we see that z divided by z again looks like a fraction, and the result is rational. If we look, we see negative 4 and negative 2 are integers. When we divide them, we get 2, which is an integer. Negative 8 and 2 are integers, and when we divide them, we get negative 4, which is an integer. But if we took 1 and divided it by negative 4, we actually get negative 1/4, which is not an integer. The last operation we discussed is exponents, and we see that z raised to the power of z is equal to q as well. Now this is something that the students need to have a strong understanding of the exponent properties to really be able to answer this question. So if we take a negative number and raise it to a power of 3, 3 being an integer, we see that negative 2 raised to the third power is negative 2 times negative 2 times negative 2, which is negative 8. We see that negative 2 raised to the second power is negative 2 times negative 2, which is positive 4. However, if we take 2 and raise it to a negative power, we see that we get a reciprocal, because the negative power is an inverse. So we see 2 raised to the negative 2 is 1 over 2 squared, and 1 over 2 squared is 1 over 4, 1 over 4 not being an integer.